Hey all you cool cats and kittens. Today we're going to wrap up the waves unit by talking about three quick sort of vocabulary terms or things that waves do. You got to know what they are, be able to identify them, and sort of explain them, and that's going to be it. So we'll start out with the Doppler effect. The Doppler effect is something that you've seen all the time. It's like, you know when you're, I don't know, like by the side of the road waiting to cross the street or something, and a car zooms by you, particularly if they're like blaring their horn, you hear that like noise as the car goes by. That's the Doppler effect. To kind of illustrate, I'm sure you've seen cars drive by before, but if you're not quite sure what I'm talking about right now, it's this noise. So with the horn, you can hear it, right? As they come towards you, you hear like, and then as they go by you, it goes like, it sounds like it changes frequency. Try another one in case that one didn't work for you. So you notice that as the car drives by, you hear that like almost change in pitch as it goes. It goes, that's the Doppler effect, that sort of sound effect. So to come up with like an actual definition rather than just like a sound noise effect, the Doppler effect is this. This is going to be our definition right here. I just wrote it before I recorded today. Doppler effect is the apparent change in frequency when a wave source moves relative to an observer. The apparent change in frequency when a wave source moves relative to an observer. So you take a minute to throw that in your notes. Basically what it means is that car that just drove by, it went, it changed frequency, it changed pitch. It went from a high frequency, or a high pitch, and then right when it drives by, it turns into a low frequency, like, or a lower pitch as it goes by. That's all this is saying. There's a change in frequency when the sound source, which would be the car, moves relative to you, meaning like moves compared to you. This is caused by motion. Which makes sense because like imagine that car was just in your driveway, like honking the horn just over and over again. Would you hear that sound effect? No, because it's not moving. You just hear that same pitch or that same noise from the car over and over again. So again, it's caused by this motion. And the word we have for that is the Doppler effect. When the car moves towards you, what did you notice about the frequency? Did you notice it was higher or lower? Again, just kind of think of the sound effect in your head. When it's moving towards you, as the car moved towards you, I think the frequency you noticed was higher. Oh, I scratched my screen. That was bad. I wrote with the pen instead of the stylus. Okay, has a higher frequency when it moves towards you. That's the part of our thing. So when it moves towards you, you have a higher frequency, which just as a reminder means you have a higher pitch. Pitch means frequency, or like that's how we detect it. So higher pitch. When it started moving away from you, this is a part of our motion here. When it moves away, you should notice a lower frequency, which equates to a lower pitch. Oops, messed up. So moving towards you, that's a higher pitch. Moving away from you, that's a lower pitch. I think the easiest way to remember this is just like you've seen it a million times. Like just remember that noise as a car drives by you. I'm gonna play those one of those same videos again, just so you can I don't know, like take a look for it this time. As the car moves towards, we have a higher frequency, and once it passes and starts moving away, you should notice a lower frequency. So hopefully you caught it right, like about here as the car is about to drive by. So you go from high frequency to low frequency, it's moving towards versus away. What actually causes that is essentially this. You have a wave source. Come on. Okay, so we have a wave source. In this case, it's a plane instead of the car. But the plane is traveling towards the right. Now, if you imagine you were a person standing here, like in front of the plane, what do you notice about the spacing of the waves in front of the plane? Well, it looks like they're really close together. And that's just because each time the plane releases a wave front, or each time it releases a sound wave forwards, it like moves forwards trying to catch up to that sound wave. So it like releases a sound, then moves towards that, and then it releases a sound and moves towards that. And what that does is it squishes together these waves in front of the airplane, or for the one we just looked at, it was a car. And since they're very close together, they'll hit you very frequently, like very quickly. The timing would be very fast. And that's what pitch is this frequency. So you would notice the frequency seems to be higher because the waves reach you at a faster pace. Now imagine you were a person behind the plane, like back here. If you were behind the plane, each time the plane releases a sound wave that moves backwards, the plane then moves away from it and releases another sound wave, and then moves away from it and releases another sound wave. So the spacing behind the plane becomes like much, much wider, which you can kind of see here. And if you imagine that you're back here listening to these sound waves, what you would notice is each time there's a sound wave, this big long space means there's a big long time for each next sound wave to hit you. They do not hit you very frequently. So you have a lower frequency, which would mean that you notice a lower pitch. And so that's it. If you're just in front, these waves have it like bunch up. If you're behind, they're spread out, which means they'll hit you in front of the plane more frequently, or behind the plane less frequently. And that's why you notice something different if it's moving towards versus away from you. So, at this point, the types of questions you'd be able, have to be able to answer are like 16 and 17, dealing with the Doppler effect. Again, as long as you know the Doppler effect is this high pitch towards, low pitch away, you can get through these. Pause the video and try these. I'm going to go over them in a second, but give this a shot. Alright, hope you tried it. 16. A crazy person who is playing his guitar while riding a motorcycle at 45 meters per second. Because you'd have to be crazy to play guitar while riding a motorcycle. The note played by the crazy person has a frequency of 440 hertz. An observer on the side of the road hears a frequency of 430 hertz. Is the crazy person moving towards or away from the observer, and how would you know? Okay, well, let's look at our frequencies that I gave you here. I said that we've got a frequency being played of 440, but what you're hearing is 430. That's a little less. It's a slightly lower frequency or a lower pitch. So if you picture that lower pitch or the lower frequency is when the car was moving away from you, like after it passed and was going further away. So it must be moving away. And the reason we would know that is what we hear is a lower frequency. So, again, since we hear a lower frequency, we know that the object is moving away from us. 17. When a wave source is moving towards an observer, the observer notices a frequency that is, alright, towards is the, you hear the higher, when it's moving towards you, you hear that higher pitch, or the higher part of that frequency. So the observer notices a frequency that is greater than the frequency produced by the wave source. So towards is a higher or a greater frequency, and away is lower. And that's the Doppler effect. So, I don't know, anytime like a car or a fast-moving object goes by you, you notice this, so think about it. It's that higher frequency towards, lower frequency away. Cool. Next up, resonance. This is sort of the weirdest one that we're going to cover. Resonance is this sort of like weird, unique property that items have when they interact with waves. Resonance is when an object is exposed to its natural frequency, and this is the big sort of phrase when you deal with resonance, natural frequency. When an object is exposed to its natural frequency, it can absorb that energy and will begin to vibrate. So objects have this sort of when I say natural frequency, it's like a built-in frequency that it sort of naturally responds to. And it has to do with a lot of things about the object, like its shape and what it's made out of, its size, so there's like a lot that goes into that. If an object is exposed to that frequency, just the right frequency, then it can absorb the energy from those waves. That energy will sort of build into it. It absorbs that energy, and it begins to vibrate. And one thing that's important is it has to be just the right frequency. If it's a slightly off frequency, then this won't work. So, if the frequency is just a little bit off, it won't work. The best example I can think of is like imagine you're pushing someone on like a swing set, and you have to push with the right timing. Like as the person goes by you, that's when you push. If the person's coming towards you and you just push into them, your timing was off, and you're not going to make them like absorb your energy and go higher on that swing set. And similar sort of thing happens for this resonance. So examples of this happening is you kind of see before in like cartoons and stuff. You know when like someone like sings like a really high note, or there's like a high pitched noise and all the glass in the room shatters. That's a real actual thing, and it's called and that's an example of resonance. Glass has a glass object like like an actual glass you drink out of, could have like a certain natural frequency, and if you can expose it to that by like singing that note or producing that pitch, then it will absorb that energy and begin to vibrate. But glass isn't really meant to vibrate. It's not really known for being a flexible thing. And so here we're going to look at a video of exactly that happening. I'm going to pause it before it gets too noisy. But what we have here, this is in slow motion so that you can kind of see it. But this is a speaker, this little hole in the thing right here. And it's producing a sound that goes into this glass. And if it's just the right frequency, then that glass will begin to vibrate. So you can see the edges of the glass start to like vibrate back and forth. This right here is a little piece of paper that was put on it, just to like, so you can see it jump up and down as the glass vibrates. And if that vibration becomes strong enough, what you should notice is the glass will actually will eventually break or shatter because those vibrations become so strong. So you can see the glass vibrating really violently, and eventually it'll shatter. And there are people, if you look this up on the internet, there are people who can do that with their voice. They can like sing into the glass and do it. So if you're looking for something to do while you're bored, you can look that up. Now I did say that timing has to be like just right and just perfect. So here we'll kind of look at why. This is just another person who shatters glass with the speaker. And again, in slow motion, you can see the glass vibrating. Now, towards the bottom, they're going to show these wave fronts coming out. And you see how the timing of them is like just perfect to push the wine glass, meaning like every time it stretches downwards, that wave pushes it forwards. When it stretches down, the wave pushes it forwards. When it stretches down, the wave pushes it forwards. That timing is like just perfect to like cause this, again, just to go backwards, to push this upwards with just the right timing, then push it upwards with just the right timing, and then push it upwards with just the right timing. And that timing, that's what frequency is. It's the number of times this happens per second. If that timing is a little bit off, then it's not going to like reinforce this motion of the glass and cause it to get bigger and bigger. It'll just kind of cancel it out, and it wouldn't vibrate at all. So that natural frequency, having just the right frequency, is everything when we talk about resonance. So what we're really looking for to identify an example of resonance is that natural frequency causing things to vibrate. And the last video I've got is kind of a cool one. It's the Tacoma Narrows Bridge. It's like a famous example of resonance. What you're looking at here is a bridge that was built in the 50s. And basically what happens is this is an object, and objects have a certain natural frequency. But it turns out that the natural frequency of this bridge perfectly matches the natural frequency of the wind gusts that blow through this particular sound. I think this is the Puget Sound over by Seattle. And what you can see is this motion of this bridge is not supposed to do that. And it is a real bridge that people actually crossed for a while too. And each time that This bridge like vibrates one way, the winds push it back, which causes it to get bigger and bigger and bigger. Again, like the swing I mentioned before, it's like pushing your legs out at just the right time to make you swing higher and higher and higher. And you can see there's like a person on the bridge. People apparently didn't mind this too much. There's some cars out there. And again, what's happening is the wind is just perfectly matching the frequency of this bridge, causing it to resonate. So this is resonance, having that perfect frequency. Here's this guy trying to walk off. I'm going to fast forward a little bit. He's fine. But the bridge does eventually collapse. They had to replace it with a different one that was obviously built better. So these architects learned their lesson, I guess. I'm jumping like this dude running away. Anyway, that's resonance. Last up for today is diffraction. So diffraction is just another thing that waves do. So waves have this ability to do something where they can bend around, this is written pretty badly, bend around barriers or obstacles. Bend around barriers and obstacles. So, think of it like this. Sound is a wave, right? So what sound does is anything that waves can do. And let's say you're in a field and you stand behind like a tree. So there's like an obstacle there, something blocking you. And someone's on the other side of that tree like yelling at you. You would be able to hear them, right? Even though there's a tree blocking your path. The reason you can hear them is because the waves bend around that tree. They bend around that obstacle. We call this diffraction. So waves have the ability to bend around barriers and obstacles. The most diffraction will occur when this right here, probably should have written out if you're copying this down in your notes. This right here is that symbol lambda, which just means, remember, that's the wavelength. So if that'll help you remember it better, then write out the word wavelength. Works best when the wavelength is really, really long and the opening is really, really narrow, the opening through which the waves are traveling. So the most diffraction will occur when the wavelength is much larger than the opening. So you'll often see a drawing that looks kind of like this. You can have a bunch of wave fronts that are approaching some sort of obstacle or barrier. So I'm just going to like have an obstacle. Let's color that in here. Okay, and when the waves reach that obstacle, here's what would happen if the waves did not diffract. If the waves did not diffract or bend through it, then the waves all the way on this region, see the part that's going to hit the obstacle? And then the wave on this part would get blocked, and then the wave would just go like this. But that's not what happens. The waves sort of bend around that opening. So what they actually do is they make a pattern that looks kind of like this. They bend around the opening. So if you were a person that was like, let's say these are sound waves, and you're like shouting through a doorway. So all these waves reach the doorway, and once they go through the doorway, they bend around it. So let's say you were like, I don't know, a person like standing over here. You could still hear the sound through the doorway, because once the waves went through the doorway, they bend around it. And the word we have for that bending is diffraction. So what I'm kind of trying to illustrate is something like this. So I'm going to clear out these waves and stop it for a second. We've got a bunch of wave fronts coming in from the top, and they're just moving downwards. Here we've got an obstacle, this thing right here that I can kind of move back and forth. We've got this obstacle here, and then the waves are going to hit it. Now when they do, it'll block a bunch of the waves. Like it'll block the waves here and the waves here, but these waves, once they go through the obstacle, will sort of bend around it. So you end up with this pattern that looks kind of like this. So if you were detecting these waves, you know, if you were all the way here on the left or all the way here on the right, you would still be able to notice those waves in those points. This is an overhead view, which looks a little different. I'm going to change it to like the 3D view and then start it over. So we've got, from the side, you can see all these waves coming in. And again, once they hit this opening, they're going to bend around it or diffract through the opening. And again, see how they sort of like bend out in this semicircular type of pattern? The word we have for that is diffraction. So you just have to understand that word know what it means. It's this bending around the opening. Now, this is something you can observe sort of like in everyday life here. So here's a couple of pictures I've just pulled from the internet of like waves approaching barriers or like jetties, which are like rocks that you put out in the ocean to stop the waves from coming through. But it doesn't totally stop them coming through because they diffract once they reach that opening. So here you can kind of see let's go with a bright color here. Here you can see the waves kind of coming in this way. And once they go through this opening, right, the opening, which is right here, you can see like these rocks. Once they go through this opening, they diffract or bend around it, and you end up with this sort of like semicircular type shape to it. That's diffraction. You're just looking at these waves, and when they come in, they bend around. Again, diffraction. I'm just saying the word a lot, so you remember it. And let's write it out. Diffraction. It's this bending through the opening. Here's another good one. This is just something from Google Images. It's like a beach that we have here, and here's some jetties. Again, just like obstacles that you put down to slow down the waves and reduce erosion, stuff like that. And you notice that as these wave fronts kind of come in from the ocean, they sort of bend outwards or diffract through the opening, which causes this sort of neat like erosion pattern that you have here. Again, the word we have for that is diffraction. It's this bending through an opening. But the other sort of fact that you need to know about diffraction is that you have the most diffraction when the wavelength is much larger than the opening. So if you have a really, 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 really long wave and you're trying to fit it through a really, really tiny opening, that's when the wave will bend the most. Like it's really squeezing through the opening before it bends around. So a long, 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 long wavelength or a small, small, small opening would give you lots of this bending. If you have a tiny wave going through a really wide opening, it just doesn't have to like bend a lot once it goes through the opening to get through it. To get some practice with that, I want you to watch this video here that I have linked and answer the questions as you go. I'm going to go over them, but I think it'll, I want you to watch the video and kind of look at it. I don't think I have you watching the whole thing, just like the first minute and a half or so. So pause this video, open up the link, and kind of follow along with the questions. The questions are to kind of get you to focus on the important points here. Alright, so you should be, hopefully, you pause the video and tried this out, and you watched the most British guy ever put together his little wave demonstration. So let's run through these. For F, I don't know why it's starting at F. I think I messed up. At the 22nd point in the video, the narrator adds 2 panels to the opening. Now that the opening is more narrow, the waves spread out in the region after the opening. What is the word for this? So we're looking at this part in the video right here. I don't know that he mentions this directly in the video, but it is in the title, diffraction. So that is what I'm looking for here. And again, if I pause this, you see how they go through the opening and begin to bend around it? The word we have for that is diffraction. So that was all I was looking for there. We're going multicolor here. Alright, at the 52nd point in the video, the narrator makes the opening more narrow. Does this increase or decrease the amount of diffraction? So at the 52nd point, notice he makes this opening really, really narrow, and I think he kind of narrates over it, but you should see like how this bending is more apparent. See how it like goes like all the way from over here to like all the way over here? That's definitely more than it was before, because see how it like kind of had this sort of narrow cone to it that he has outlined? Here, that cone would be much wider, so you should notice that hopefully it increases the amount of diffraction. Again, the idea is that when the wavelength is a lot bigger than the opening, there's more diffraction. So if the opening's small, then you should have more diffraction, because it sort of increases the size of the wavelength in comparison. And just to make it like a little more obvious here, we're going to jump to the 1 minute 6 second mark, which is right about here. And he makes the opening very, very wide. And what does this do to the amount of diffraction? Which is just the amount of bending that occurs. So what you should notice is if we pause it, like here, I think we have a lot less bending. Now I know, like, see how we have this sort of wide column, like over here? where the waves are mostly flat. That's not quite diffraction because it's bending, but like see how like little it bends? It's just this tiny region of space where the wave bent around. So hopefully what we're looking for is that there is less diffraction as the opening gets wider. Again, I hope you watch that on your own and answer the questions, but if you had trouble with it, that's that. If you still don't understand, go back, rewatch the video one more time, and look for these things. So you should be able to answer questions like numbers 19 and 20. So pause this, give them a shot. Basically, I could reasonably ask you to draw diffraction, and I could reasonably ask you the effect of the wavelength. So pause this and try those. The diagram to the right shows four wave fronts approaching an opening in a barrier. The width of the opening is approximately 1/2 the wavelength of the waves. On the diagram, draw the shape of at least 3 wave fronts after they pass through the barrier. This just comes down to being familiar with the diagram, and I showed you the videos, and then those extra pictures, and then the that simulation thing. We're just looking for, it says how many? 3? 3. So 1, 2, 3. There we go. That's it. Once the waves go through the opening, they bend. That's it. That's all we're doing. Cool. The diffraction effects of a wave passing through a barrier are most noticeable when the wavelength of the waves... So we said when the wavelength is much, much, much bigger than the opening. So when the wavelength of the waves is very long, because you'd have like these big long waves trying to fit through an opening that is very narrow. And that's it. So what we did here was we did Doppler effect, which is... You have to know that towards you is a higher frequency, away is a lower frequency. We did resonance, which is objects have a natural frequency. And if there's one phrase there to keep in your head, it's that natural frequency. When exposed to the natural frequency, objects begin to vibrate, as long as it's just that frequency. And lastly, diffraction, which is waves bending around an opening or around an obstacle. Diffraction is most apparent, or like most present, when the wavelength is much, much bigger than the opening. So long wave, small opening. And that's it. That's our waves unit.